Okay, can you guys hear me okay? All right, thanks for having me, everyone. I'll start by saying GOTO is a great conference. I've been a few years before, and so if you don't have a ticket already, highly recommend going. So I'm going to talk about transactions today, specifically embracing transactions. I think transactions are a really useful building block for applications, and I want to show you how we can take this idea of being able to compose transactions together, sort of try and take it to its natural conclusion, see how one implementation goes, and explore what some ideas around this really simple concept is. How many of you have or are using a relational database at work? Okay, so a lot of people. How many of you use an ORM? Oh, I would have expected a lot more people. How many of you write raw SQL? Okay, so there's going to be some raw SQL ahead. So if you use an ORM, be prepared to close your eyes. So we're going to start with a simple question. Do transactions compose? Anyone have an idea? Okay, I think they do, but let's see. So let's kind of break this out and see exactly what we mean by transaction and composition. What is a transaction? Anybody have a thought?
An atomic unit of work?
Yeah. Compose. Compose comes from composition. So if we dig into transactions more, we see this word ACID come up, especially with relational databases. And in particular, when we're talking about transactions, we're really thinking about atomicity. The rest of these are nice properties for the entire system of a relational database, but for an individual transaction, sort of just from our point of view, not thinking about concurrency or anything like that, we're mostly interested in this word atomicity. And this kind of breaks down into atomic, which comes from the Greek word atomos, which means undividable. And so a transaction is something that cannot be divided into further components. The entire transaction is either going to complete successfully or roll back and not complete at all. And in general, this idea of being able to do atomic work is a really important building block, especially with things like databases and concurrency. Because we want to be able to do some set of actions, compose or group them together, and be able to know that the entire thing is going to complete at once. How many of you have done some database transformation, maybe even on like a NoSQL database, or written a bug in your code that left the database in some inconsistent state? Yeah, I've definitely done that like 100 times. And so atomicity is a really important component for this because it allows us to say, I want to do all of these things at once, and all of them must complete or none of them must complete. There's no way that we can onboard a new customer, create an organization for them, create the user that's going to go in the organization, and then like not put them in the organization, which means that now we have to go write some script to fix up the data, and then if you're me anyway, there's a bug in that script, which makes things even worse. And so I think atomicity, especially when dealing with business critical data, is an important thing to consider. What about composition? What does it mean to compose things? Typically we think about putting things together when we compose. And so we might have two things, and here we've got some circles, and when we compose them together, what do we get? Another circle, right? A bigger circle. And if when doing this, we've now made this atomic, it means that we can't sort of peek under the hood and see, oh, that's actually two circles together, and I can commit one of the circles but not the other. If we think about functions, the composition function is going to take two arguments, two A's, doesn't matter what A's are, and it's going to return a third A. So this is just a binary function that takes two parameters of the same type and returns the same thing. Function composition is composition, right? We take G and F, that returns a new function that's first going to call G, and then going to call f. But once we have that, there's no way to kind of like peek inside and see what the two functions are. There's no like explode to source code, kind of thing in most of our languages. Addition can be thought of as composing two numbers together. So our a's in this case are going to be integers, and then when we compose two integers together, we get a third integer. So anyone have an idea what happens if we compose two transactions? What do we get out?
Another transaction.
Another transaction, right? So this is useful because we can now say, I have these two reusable building blocks, which are each transactions. These things are each indivisible. I can execute them and know that the database can't partially commit one of these. But I can also now compose them together into a larger transaction, which itself can't be broken down. Seems like a pretty straightforward thing, right? So, yep, we get another transaction. But it turns out that trying to actually put this into code is a little bit more difficult than I've made it sound so far. So let's run through an example. We're going to create a really simple table. It's going to have two columns. It's going to have a name that's going to represent a city, and then it's going to have the continent that the city goes in. So Chicago, North America. And here is some of that raw SQL I was talking about. So we're going to insert in a new city, Chicago, North America. Is this a transaction?
Yeah.
I think it probably meets our definition. This cannot be divided up into further work, right? And if we execute that and then we ask for the state of the database, we say, okay, there's one row, Chicago in North America. What about this? We're going to now create Chicago, New York, and San Francisco, all North American cities. Is this a transaction?
No.
No. And that's because we could do this first part of the transaction. We could create Chicago. Something bad could happen. There could be a power outage on the database, and this first row commits. There could be a programmer error. Or the power could go out on the app server. And in a lot of cases, this works fine. But saying we have this foo syntax error here, if we run this, it happily adds New York and Chicago to the list, even though there's an exception here, and then San Francisco is left not included in our list, not willing to relocate to San Francisco. So this leaves our database in an inconsistent state compared to what we were trying to do, which is bad. How about this? Is this a transaction now? There's a begin and a commit at the top and bottom now. So I think that this is a transaction. Let's see what happens. So we're going to introduce our same foo syntax error. This could be anything. It could be an exception in your programming language or some network connectivity fail. And so when we run this, Postgres or whatever database we're using is going to happily start a transaction, insert Chicago, New York. It's not going to show anyone else just yet. We're going to have our error, and then we're going to actually roll back this transaction and never commit it. And so if we run this, nothing has been done. That set of inserting 3 cities is undividable, right? So that's good. So I think that a transaction is a begin statement followed by a series of other statements followed by exactly one commit. This is pretty simple, right? Mm-hmm. Okay, so now we have 2 transactions that we want to compose together. Foo is a transaction because it's surrounded by exactly one begin and one commit. And bar is a transaction because it's surrounded by one begin and one commit. But if we were to just sort of execute them in linear order like this, that's actually 2 transactions, not one composed transaction. So to compose these 2 into one transaction, what does that look like? Well, we have to get rid of this commit, the second, this first commit here, and this second begin there, and have begin foo bar commit. Okay? All is seeming pretty sane so far, and if you were sort of just writing these out by hand and not calling into some helper functions to create New York, create Chicago. This is pretty simple, and you say, of course, I'm only going to have one begin at the beginning, one commit at the end. And so we say that a transaction is something where the statements are always run in a transaction. So if we call something a transaction, you can't execute the code not in a transaction. Seems pretty tautological. And if we compose with another transaction, there is exactly one begin and one commit, right? And so if we call something a transaction, the statements must always run in a transaction. And so we are a developer, and we're starting to write some reusable functions. We're going to stop writing exactly raw SQL and use Python that's going to send some database statements to Postgres or whatever our database is. And to do that, we're going to write ourselves a little helper function that allows us to say with transaction. And this is going to take care of running our code in exactly one of those begin and one of those commits. And so if you're not familiar with Python, this is basically allowing you to say, I'm going to create this thing that we're going to call a with statement. We'll later be able to say with transaction. And it's going to call begin, then it's going to call whatever code you pass in. If there's an exception raised, we'll call rollback. And if not, we'll call commit. So this is pretty straightforward so far. And now we're going to define a function to create two of the cities that the GOTO conference is in. So Chicago, which is in North America, and Copenhagen, which is in Europe. And so a transaction always has a begin and a commit, and we can't call this a transaction without that. And so we are careful developers because we don't want to expose this not inside of a transaction. It's not a transaction if you can create Chicago and not Copenhagen. So we say, define this function, go to cities. We'll call with transaction, which is going to take care of rolling back the transaction if there's an exception, and basically just remove the boilerplate of us having to remember to call begin and end. If you've used a database driver before, you've probably used something like this as well. So first we're going to insert Chicago and then Copenhagen. And if we execute this function in Python, it turns out we can actually inspect exactly what Postgres sees. So there's a log option we can turn on, and we can just look at the log files, and it will just echo back every single literal statement that we send to Postgres. So this kind of allows us to peek behind the scenes and see exactly what the database driver that we're using is doing. So first it's going to call begin. It's going to create Chicago, then Copenhagen, and then commit. Is this a transaction?
Yes.
Yes. Okay, so we're good here. We've now created this hopefully reusable transaction that is a function we can call, which will create two of the GOTO cities. Okay, now we're going to create two cities that I wish GOTO were in. So I really want to go to Tokyo and South Africa, which are in Asia and Africa. So now this is another reusable function that we can call future GOTO cities. And inside of a transaction, it's going to create Tokyo in Asia and South Africa on the continent of Africa. And so I claim that this is a transaction as well. These statements are in exactly one begin and one commit. Now, what happens if we want to combine them together? Is this going to be good or bad?
If it's composable, it should be fine.
So we're definitely in a transaction. We're in like 3 transactions, because GOTO cities calls with transaction, future GOTO cities calls with transaction, and with transaction definitely calls begin and commit. And so we're extra safe, right? There's like no way that this could possibly not be atomic because we're in so many transactions. Sadly, that is not what happens. And I will tell you that if you are doing this, almost certainly your database driver will happily send exactly these statements to Postgres. And if you're not looking at your logs, you'll have no idea what's going on. In fact, I did stuff like this for a really long time, having no idea that there's a super subtle bug here. So what ends up happening is we call begin from the first with transaction. And then we call GOTO cities, which also is going to call begin. So we begin again. Insert Chicago, Copenhagen, GOTO cities completes, which says, oh yeah, this completed successfully with no exceptions, so we should commit. And then future GOTO cities is going to call begin. We'll insert these two cities. Future GOTO cities with statement's going to end, it's going to call commit. And then this outer with transaction is going to call commit. And this turns out to have an issue. And so if we actually look at either the warnings that our database driver may or may not give back to us, or the logs in whatever database you use, you'll likely see something like this. There is already a transaction in progress, and there is no transaction in progress. And I'm kind of embarrassed to admit that for the first few months of seeing this, I was like, that's just some bug. And then I just started getting super curious, that doesn't quite seem right. Okay. And so there's actually a really logical explanation for this. If we go back and look at exactly what we're sending the database, we call begin twice. And it turns out that most databases don't implement anything that we would think of as nested transactions. Or if they do, it's really not what we want. We don't want to nest these transactions. We want one big transaction that creates New York, Chicago, Copenhagen, South Africa, and Tokyo, right? And so if we just go into a Postgres shell and we type begin twice, the second time Postgres is you know you're already in a transaction, so I'm just going to ignore this statement completely. Then you call commit again. It's okay, we're in a transaction, let's commit. And then you call commit the second time, and you're not in a transaction anymore. And so there's this little annoying bit in between here, those two commits, where you think that you're inside of a transaction, but you're actually not. Postgres doesn't raise any error or anything. It just says, okay, but I can't commit anything. And so if we try and run this code and we raise an exception here, what we'd like to happen, what we're trying to achieve, is that this entire set of statements is going to complete atomically, right? We're going to insert New York and Chicago, or Copenhagen and Chicago, and then Tokyo and South Africa. And we think that happens because in that little function we wrote, if there's an exception, we call rollback, right? Well, let's see what happens if we actually execute this code. We call begin twice again. We insert Chicago and Copenhagen. Then we call commit because we do successfully complete from GOTO cities. So now that's in the database. The transaction's over. Then we raise this value error, but we're still inside of, well, we think we're inside of this transaction. So our Python code says, okay, roll back. So we roll back, but we've just rolled back a transaction that hasn't actually done anything because we've already committed this first one. And so if we ask what's in the database, we get Chicago and Copenhagen. And so it's now seeming difficult to create these little reusable functions that if you use them on your own, there's no way to not run it in a transaction, but to also compose it to create bigger transaction. It's feeling like these things are kind of at odds with each other, right? And so we have met this first part. The statements are always run in a transaction. And for a while, what I was doing is sort of saying, I have to either kind of be lenient and say, put in some documentation and say, okay, this is some reusable SQL code, but you as the developer, when you're ready to finally put this in a transaction, make sure you wrap it in a transaction. And that's kind of unsatisfying because we don't like to rely on comment convention to convey things like transactional integrity. That's a little scary. On the other hand, we could wrap it in a transaction and put a comment that says, don't try and compose this with any other transaction. But that's also just a comment, and we saw what happens if we do compose it with another transaction. It doesn't actually compose into a bigger transaction. And almost worse, you get this situation where you have this false sense of confidence that you're saying, okay, there's like 4 with transactions, so this is for sure in a transaction, but it's actually not. And so we're kind of left in this frustrating situation that we know what we want, but we're having trouble teaching this higher level language how to translate into SQL. And so when we compose with another transaction, we want exactly one begin and exactly one commit. Remember?
Right.
This is what's proving difficult. And just to kind of drive the point home, this is kind of an illustration of the situation that we're coming into. We have this first begin in the outer with transaction, and then we have a few other begins that Postgres is going to say, yeah, whatever. We're going to write Chicago, Copenhagen, but then because we called with transaction on GOTO cities, it's going to commit. Now the transaction is over. This is not indivisible. This is a dividable unit. Then we call future GOTO cities, and probably 99.9 whatever percent of the time, this works fine. And then we have that one situation where we're like, how the hell did the database get in this state? I use transactions everywhere. And it turns out that there is a solution to this. It's remarkably simple. Sadly, I'm going to show it to you in Haskell, and so questionable how useful it will be to all of you. But I think the basic point will be driven home, and hopefully you'll think, oh, it's pretty cool that Haskell can solve these kind of problems in a really simple, elegant way. Come talk to me afterward if you do want to talk about how we might do this in Python, Java, whatever, because it is absolutely possible. Okay, so let's kind of translate our Python code that we had before into Haskell. This is just the type signatures. We don't have to look at any actual Haskell code. And so create GOTO cities is going to be a function from connection to what's called an IO unit. And this basically says this Haskell function can interact with the outside world, and it doesn't return any meaningful value. We're just calling it for the side effects because it's going to insert these things into the database. It's not going to actually give us any results back from SQL. Same with create future GOTO cities. And just like in the Python version, in the Haskell Postgres library, there's a function called with transaction that does exactly what we saw before. It just says begin, run your code, commit. And if you nest them together, sort of inadvertently as you compose these little reusable transactions together, you get in this situation where you're calling begin more than once, and then you commit at like the most nested part of the transaction, and now your whole transaction's over. And there's a really simple change that we can make just to the types that help us out here. So types to the rescue here. So if we create this new data type, which we're going to call PG transaction, let's not worry too much about what it looks like, but under the hood, it's basically just looks like this. It's a function from connection to some IO action that we're going to execute. And we have this neat little property of Haskell, which is the only way you can interact with the outside world is through IO. And so if we have this thing that is just a PG transaction, we know it hasn't actually sent anything to Postgres yet. It might describe what we want to do to Postgres, but it hasn't actually executed yet. We have a chance to sort of sneak in and say, like, all right, we're going to insert exactly one begin and exactly one commit. And so the only way to turn this PG transaction value into an IO, because we don't export the constructor for PG transaction, you can only create a PG transaction through these helpers that we're going to give you. The only way to actually turn this into a value which will actually execute against Postgres is to call this run PG transaction function. And what does that return you? It returns you an IOA. It does not return you a PG transaction. So once you've like run your PG transaction, that's it. You can't pretend to compose it with another transaction because we've already set the begin and the commit. So this really simple change now allows us to define these reusable functions, which are built on query and execute. So it's going to take a query, which is basically just a string that we're going to do some SQL sanitization on, an input, which is just some Haskell data type that we're going to send to Postgres. It's going to return a list of output that matches our query, but it's going to do it inside of this PG transaction type and not IO. So it doesn't have to worry about sending begin and commit. We specifically don't call with transaction because there is no with transaction that works on PG transaction. Because we know that the only way that someone can actually execute this is calling that run PG transaction function. There's also execute, which allows you to insert things into the database, and it's going to give you back an integer of the number of rows that were deleted, updated, or inserted in. And so now we can create these reusable functions to create GOTO cities, create future GOTO cities, and they're going to run in this PG transaction type that we've created. We can now rest assured that if somebody successfully executes this against Postgres, the only way they can do that is by calling run PG transaction, which is going to put exactly one begin and exactly one commit at the end. And once they've done that, they can't do anything else with the database for this transaction. A new transaction is going to start. And so the author or the developer who actually calls this sort of has to decide how big of a transaction do I want to compose. And once I've done that, I've sort of agreed, okay, I'm not able to compose this with any bigger transactions anymore because it's not possible, right? So we can now say create all cities, which is going to be a function. This is not a reusable transaction because it returns this different type. It does not return PG transaction. The types tell us that we can't even pretend to compose this anymore. We're going to call run PG transaction, pass in our connection, and now safely and exactly one begin and one commit, we can create GOTO cities, create future GOTO cities, and nothing is really lost to us as a user of this. We're just using query and execute as we thought we were before, and we create these reusable components. Another kind of cool thing falls out of this. Do you think it's a good idea if you open a transaction and then sit with the connection open for 15, 20 minutes? No, but I have definitely done that before. You're like in some transaction, you don't even realize it, and you're like, I'm going to make an HTTP request. And then it times out after like 20 minutes, and the database load is at like 24 on a 24-core machine. And it's because you have this long-running transaction open inadvertently. Because inside of a transaction, your database still has resources associated with this transaction. It's keeping like its own special isolated view of whatever part of the database that you're touching just for you, the special view just for you. And you're off making HTTP requests. And so these types actually allow us, if we want, to prevent us from doing that. So if you want to be able to do HTTP requests inside of a transaction, you can sort of give yourself that permission by making a slight change to this. But if you want to be able to say, once I'm in a transaction, all I'm going to do is talk to Postgres as fast as I can, commit the transaction, not leave these transactions open, then you can actually use types as well to eliminate this entire, honestly, tough to diagnose situation where you have these long-running transactions where you might have touched or queried a table that has 500 million rows, and the database is keeping this special resource-intensive view of it for you, while you're off doing something that you don't even care if it's in a transaction. You just kind of made a mistake. A very easy mistake to make as well. And so the Haskell code I've just shown you is in an open source library that we've created at the company I work for called Helium. So if you want to check it out, the whole thing is like 70 lines of code, including a lot of kind of boilerplate that just maps the normal Postgres query functions, query, execute, little variations like that. The core code is honestly like 4 lines of code that does this whole thing. And exercise left to you all to think about this in Python. It will not be as elegant, but I guarantee you it is also possible to do this in whatever your favorite language is. So come chat with me afterward if you're interested. Thank you very much. Do we have time for questions? Yes.
Yeah.
Helium's the company I work for.
It's gonna
Yeah.
be the best.
Oh, what do we do? We are an Internet of Things startup based in San Francisco. I'm local to Chicago, but the company's based in San Francisco. Basically what we do is we make it really easy for other companies to create their own sensors. So we have physical sensors that are battery powered, which connect back to our network. And you can send Lua code to those sensors and create production sensors that use an analog digital converter or a GPIO and write production quality sensors that have a battery life of 1.5 to 3 years by sending your own Lua code down to these. And then on sort of the platform side, you can do all sorts of interesting analytics, data storage, and processing with that.
Are there IP addresses attached to those sensors?
There is a MAC address, yeah. Yeah.
Do you have any opinions on how frameworks like Spring solve this problem by basically instrumenting around method calls and using thread local variables to detect whether or not a transaction is already present?
Yeah, so I can't speak specifically for what Spring does. I imagine several frameworks do probably kind of solve this, although I will say several that I looked at. So I originally kind of wrote all the code examples in Haskell, and I was like, yeah, maybe that's not a very good idea. And so I started writing in Python, and so I did exactly what I was saying before. I wrote a little Python program, and then I looked at exactly what the Python driver, PsychoPG2, I think it's called, which is like the Python driver that everyone uses, does, and it does the naive thing. It actually does something slightly more nefarious, which is that if you're in a nested transaction, it's like, oh, you're already in a transaction, so I won't call begin again, but then it calls commit. And so I had to redo the slides. It was like, that's even more confusing than just having like pairs of nested begin and commit. Yeah, I mean, I think somewhat sadly, this is the kind of thing that like you find out by looking at some bug report in whatever framework you use. Anyone else? Cool. Well, thank you very much, and I'll be happy to talk with people more in person if you want. Thank you.